Hello, it's lecture 3, stat 135. Last time we started section 7.3.1 showing that the variance of the sampling distribution is sigma squared over n times this correction factor n minus n over n minus 1. Well, today we're going to finish that, and then we're going to also look at an estimation of the population variance. So sigma squared, generally we don't know, and we need to estimate that. And then we're going to start chapter 8, which is about estimating parameters and fitting probability distributions. So last time we looked at annual income of households, and we had a population size capital N, where capital N is the number of households in the US, and we took a sample size small n, and this was a simple random sample. And these XIs, capital XIs, are uniform on all the household incomes. So in other words, X1 is we're reaching into a box with all of these different tickets, and it's what we get, and so on. So facts about uniform distributions are that its expectation is the population mean and its variance is the population variance. And what we're interested in is the variance of X bar. So as a first step, we're going to look at the variance of the sum of the XIs, which we'll call T. And this is a sum of covariance terms because these XIs are dependent on one another. And we have n squared pairwise covariance terms. The diagonal ones, in other words, when I is equal to j, these are variances. And the off-diagonal ones, the n squared minus n off-diagonal terms, are covariance terms. And the property of covariance is that it's symmetric. So covariance of x1 comma x2 is the same as covariance of x2 comma x1. So in fact there are n squared minus n of those, and they're all the same as covariance x1, x2. And similarly, all the different variance terms are all the same as variance x1. So in fact, the variance of t is just n times sigma squared plus n minus 1 covariance x1, x2. And we need to find the covariance of x1, x2. So we do a trick. We say, okay, let's imagine that our sample is the entire population. So then we're drawing all the tickets in our box, and so the sum of all those tickets is going to be the same always, right? Even if we draw those tickets out in different orders, we're always going to get all the tickets. So the variance is going to be 0. And so we can write out our expression for the variance of t so that we can solve for the covariance of x1, x2. And we see that the covariance of x1, x2 is minus sigma squared over capital N minus 1. And then for general n, once we know that, we can get an expression for the variance of t and ultimately the variance of x bar to give us the desired formula. So to summarize, the variance of x bar is sigma squared over n when x1, xn are IID, and when they're SRS, in which case we're drawing identically distributed, we're drawing from the same box, but they're not independent anymore. In that case, there's a correction factor, capital N minus n over capital N minus 1. So moving on to section 7.3.2, which is an estimation of the population variance. So last time we saw in quote that the sample variance is an unbiased estimator of sigma squared. In other words, the expectation of S squared is sigma squared, but I sort of didn't explicitly mention this, but this is only true when x1 to xn are IID. More generally, if x1 to xn is an SRS, there's in fact there's an extra term that you have to multiply S squared by for it to be unbiased, namely 1 minus 1 over capital N. And the proof of this we're going to see right now. So here is the proof that I gave last time. I've added in red the assumption that the x1 to xn is IID. And now we're going to just require that the x1 xn be an SRS. And so now 1 over 1 minus 1 over capital N, or equivalently n minus 1 over capital N times S squared, we're going to show is an unbiased estimator of sigma squared. So you may be asking yourself, where does this capital N minus 1 over n come from? So I've just indicated in the proof from above where the change is, and so I'm just going to let you stare at this, but it's important you understand all the steps, okay? So the key results of Chapter 7 that you need to know are highlighted in this table on page 214. We're certainly not covering everything in Chapter 7, but this is what you need to know. So the first row is where we have a population parameter of mu. Our unbiased estimate is x bar, and the variance of x bar is sigma squared over n, n minus n over capital N minus 1. So clearly we're assuming here that we have an SRS. Now, most of the time we don't know what sigma squared is. So if you look at the fourth row of this, this says that 1 minus 1 over n S squared is our estimate for sigma squared. We know from above that this is an unbiased estimate. And if you substitute that in for sigma squared in the first row, third column, then you'll get the estimated variance, which is the first row, fourth column. So this formula here. Okay, so this estimated variance is an approximation for the variance of the estimate. The second row follows in the same way as the first row does, and just want to note that how we're getting this estimated variance here, in the first row, fourth column, this term 1 minus little n over big N, that's coming from substituting 1 minus 1 over capital N S squared for sigma squared. And so Uncle Adam here wrote out all the details for you right below here, so you can make sure you understand that. Okay, so that's Chapter 7. We're moving on to Chapter 8 now. And here our motivation is that we have some data set from nature. We model it using some probability distribution, and later then we'll be able to test how good our model is. But for right now, what we're trying to do is we're modeling and we're estimating the appropriate parameter. So in this example, we have radioactive decay of americium-241, and this particle is decaying for 12,070 seconds. We break the time axis into 10-second intervals, and we count a total of 10,129 alpha particles. Let x be the number of arrivals in a 10-second interval, and x is a good candidate for Poisson because this alpha particle decay satisfies three requirements for a Poisson process, namely that lambda is constant, the rate, the number of arrivals in disjoint intervals are independent, and arrivals don't coincide. These are all things that are reasonable assumptions for alpha particle decay. And our lambda, our candidate for the estimate for lambda is going to be the total number of arrivals over the total number of intervals, which is 8.4 arrivals per 10-second interval. So that is 8.4. Okay, so we have our distribution for x now, and we can figure out expected values. So we have 1,207 independent intervals. What's the probability that an interval gets 3 arrivals? So that's something that you can calculate because you know that x is Poisson and you have an estimator for lambda, namely 8.4. So we can just calculate that using up the Poisson distribution, and we find that this probability p is 0.022. So if we want to calculate the expected number of intervals out of 1,207 that have 3 arrivals, what we're going to do is we're going to realize that the number of arrivals the number of intervals with 3 arrivals can be modeled as a binomial with n, the number of independent intervals, 1,207, and p, the probability of getting 3 arrivals. So we're thinking of a binary trial here, a Bernoulli trial, I should say, where each interval either gets 3 arrivals or they don't get 3 arrivals. So the number of intervals that get 3 arrivals is binomial 1,207, 0.022, and the expectation of that is just NP, so it's 27 in this case. And that explains how we get the expected column in this table here. So, for example, here we have the total number of intervals, 1,207, and we observe, let's say, 28 of those intervals have 3 arrivals, but we expect 27 because 27 is 1,207 times 0.022. If we wanted to know, for example, what's the expected number of arrivals for, what's the expected number of intervals having 4 arrivals, then we'd look at a binomial 1,207, and then we'd have a new p given by the Poisson distribution for 4, right? So that's, and then so we get 56.5 would be the expectation of that binomial, right? So this gives us now this table of observed versus expected value, and you would hope that the expected values are close to the observed table, but in fact, what does close mean? This can be quantitated using what's called a chi-square distribution and a goodness of fit test, which we'll see